What's up, guys? Today we're going to talk about heaps, and I think the best way to learn is kind of by doing, right? So we're going to start by solving a problem here, which is going to be a hard one, but I think it's not that hard actually. And it's the 295 find median from data stream. The median is the middle value in an ordered integer list. If the size of the list is even, there is no middle value, and the median is the mean of the two middle values. So for example, if I had an array 2, 3, 4, the median would be 3 because it is the value that is exactly in the middle, right? If we have an array that is 2 and 3, then the median is 2 plus 3 divided by 2, which is 2.5, since the number of elements here is even, right? So they're asking us to implement the median finder class, which initializes the median finder object, and then we add a number and find the median. So pretty straightforward, right? Actually, I think it's one of those problems that at first doesn't seem that hard, but there's always a trick to it. So kind of the first naive approach right off the bat would be, I don't know, anytime we add a new number, we rearrange the whole set again or something like that. Not pretty optimal, right? So here's where heaps come into play. But first off, what is a heap? A heap is just a complete binary tree. Complete meaning that every level is full except for the last one, which can or cannot be full. Both are valid, with one extra condition. So if it's a min heap, every node's value is smaller than or equal to their children's. And if it's a max heap, then every node's value is greater than or equal to its children. So essentially, heaps have 2 or 3 operations. The first one would be pulling from the heap. So basically taking the node at the top and getting its value. For that, we can do either pick, which is just looking at it, or pull, which is returning the value and also taking it out from the heap. This is done in of one time. And then we have the operation to add. And for that, usually what we do is we add it at the bottom and then we heapify. So we rearrange the heap again. And since it's a binary tree, with that set extra condition we set before, complexity for that is O log n. So the worst case scenario, the top node could go down from the root to one of the leaves, choosing one out of 2 paths every time. So to solve this problem, we can just use 2 heaps. We're going to use one for the upper half values of the set, which is going to be a min heap, and a max heap for the bottom half values. That way, we will always know the 2 middle values of the set, one at the top of each heap. So we're going to allow the max heap, which is going to be the one keeping the bottom half of the numbers, to have at most one more element than the min heap, keeping the top half. So let's delve first into the code. First off, we just initialize both heaps. We're going to use Java for this example, and it's just creating a priority queue. For the max heap, you also have to pass this collection's reverse order. As I said before, to add a number, we're going to allow the max heap to have exactly one more number at most than the min heap. So if the number is smaller than or equal to the top of the max heap, it's going to be at the bottom half. Else, we add it to the min heap, which means the number is at the upper half. And now we balance the heaps. As I said before, we're allowing the min heap to have one more extra element than the max heap. So if the max heap has more than one extra element than the min heap, we're going to take one element from the max heap and add it to the min heap. So what we're doing is offer, which is the operation to add, and we are adding the max heap pull, which is returning and taking out the top node from the max heap. And then if the min heap is greater than the max heap, because remember, we're not allowing the min heap to have more elements than the max heap. So if its size is more than the max heap size, then we're going to take one from the max heap and add it to the min heap. And that is pretty much it. So with this approach, finding the median is just O of 1. Because, to find the median, we just check the max heap size. If it's equal to the min heap size, we have an even amount of numbers. So we're going to compute the average of the 2 top nodes, right? We pick, remember, pick, not pull, because pull would remove it. So we just pick the 2 of them, add them together, and divide it by 2.0, because remember, we have to return a double here. And otherwise, the only remaining option is that the max heap has exactly one more element than the min heap because of what we said before. So then we just pick the max heap, cast it to double, and return it. So finding the median is of one time is just picking one or the two of the heaps, basically taking the element or elements at the top, and adding a number is of log n, which is, as explained before, the complexity to insert into a heap and then heapify. So that's been all for today. I hope you guys liked it, and don't forget to leave a like, subscribe, and follow me on X. Goodbye.